Okay, yesterday we discussed the analog and digital signals, right? So as you can see here, the analog signal is the real world signal. Okay, every signal that you see in the world is analog. So in the analog signal processing, traditionally it was starting from analog input, and you do analog processing and you get the analog output signal. However, in digital signal processing, what we do is that the real analog signal now goes into the system and goes into the A to D converter. This A to D converter will convert original analog, the real world analog signal, into the digital signal. Now it's a digital signal, so we can do the digital signal processing. Okay, you can do whatever you want with the digital signal processing, and then the output is again digital signal, because the digital signal processing input, both and output, both are digital signals, and eventually these digital signals will be converted back to the analog. Think about this one as a simple example. You get a, let's say you have a microphone, right? And a guy will speak on the microphone, right? And this microphone will get the voice, a male's voice, convert to the digital signal, go to the digital signal processing. And in digital signal processing, let's say we are changing the frequency in the digital domain. Okay, so guy's voice now move the signal to shift the signal to the right, going to the higher frequency in the digital domain. And you get the output signal, and going through the D to A, go back to the analog signal, you can get the female voice. It's like a voice disguising device, right? You speak on the microphone. In the speaker, you are listening to someone else's voice. Something like, you know what that means, right? You can do something like this, right? You get the analog signal and change it to digital, and you can do something else in the digital domain. Okay. These are some of the advantages of digital signal processing. So why we are changing the analog to the digital and do all the signal processing in the digital domain. These are advantages, right? You see that the hardware, the VLSI, is very cheap. It's very low cost. And not only that, when you have a digital signal, now you can use a memory. Right? All of the digital signals, now digital signal means that all the information is now changed to 0 or 1, so it's very easy to store into the memory. So analog, it's pretty difficult to put it into the memory, right? So you can use a memory, you can use a very cheap hardware, and also another very important thing is this one, stable, reliable, or more robust. Robust means reliable, right? So that's a very important feature of the digital signal. Analog signals, it's very easy, very difficult to handle, right? If you have some error in the analog information, it's very difficult to remove the noise or error from the signal. But in digital signals, let's say you have digital signals, you have an error on top of the signal, it's relatively much easier to remove the noise or the error component. So you can recover the original information back. That's much easier. So that's why some of that is coding. Also, compression is possible. What is compression? In the computer, you always use a compression, like a zip. You know zip, right? Something like that. That's very common in computer. What you do in compression is that you have original information, some original information, but you compress it, make it smaller, right? Why do you make it smaller? Maybe you want to save your hardware, like a hard disk storage, or maybe you want to make it small, and then after that you can deliver to someone else. If you deliver a very big one, it's very difficult to do it, right? Make it smaller and transmit. And even when you go to the web page, sometimes when you want to download something, typically that file is zipped, right? In that way, it's much easier to download. Downloading is basically the same as communication. Someone else put the file there, and over the channel, you basically download it. You are the receiver. So it's like a communication. So compression is sometimes very useful. Analog signals, very difficult to do it. Okay? In digital signals, it's much easier to do compression. So all of these benefits comes with the digital signals. Okay? So that's why we are using digital, and digital signal is very common these days. This is what we discussed last time. Analog signal is always continuous time and continuous value. Okay? In continuous time, you can typically see two different signals. One is a periodic signal, and the other is aperiodic. Periodic signal means that signal is repeated, right? Some of the period is repeating. Aperiodic means there's no period, there's no repetition. That's aperiodic signal. Okay? And most of the time that in this course, you're going to see random signals. Deterministic signal is something like there's some signal, but that's deterministic. So you know what's coming later. You can expect what is coming because it's already determined, right? After this, you always get some other, and you know what it is. It is deterministic, right? Typically, we don't see much of deterministic in communication. Typically, most of the time, we are dealing with random signals. And the best example for random signal is noise. Okay? Noise is random. And even the signal that we are transmitting is sometimes random. So most likely we are dealing with random signals. This picture shows you some simple comparison between analog and digital. As I said, this is analog signals, the left top signal. That's a continuous time, continuous value. Okay, just an example of analog signals. And the right bottom here, this is an example of digital signals. So as you can see here, the digital signals have a sample, right? Discrete time signals, not continuous, but discrete time. Not only that, you can see levels, right? You cannot have any value. You need to have value only one of these. So you have levels, right? Only these values are possible. So that's what we call as quantization, right? So you need to do quantization, meaning that the value will be now discrete. You're going to do sampling, meaning the continuous time now becomes discrete time. How often you have a sample depends on sampling frequency. How many levels you have depends on the number of bits of your quantization. Okay? So these two things, quantization, sampling, both are done inside A to D converter. Okay? That's why, as I said earlier, every A to D converter has a specification, like 8-bit. Okay, 8-bit A to D converter, meaning you have a 2 to the power of 8, like 256 different levels in that chip, in that A to D converter. Also, the converter, A to D converter, sometimes give you some specification about the sampling frequency. The maximum sampling frequency you can use is, for example, 100 megahertz, something like that, right? So both those two are the basic and main functionality of A to D converter. And this is how you can change the analog to digital signals, right? So we are getting these signals, digital signals, originally from this one. This signal goes into the A to D converter. A to D converter do these things and change analog to digital. So this is the output of A to D converter. Now this signal goes into DSP, digital signal processor. Okay? So this is going to be input to the DSP, and inside the DSP you can do whatever DSP processing you want. This slide talk about a little bit on the sampling, and regarding sampling, one thing that you need to remember, there's a Nike sampling theorem, right? The details about the Nike sampling theorem needs to be covered in DSP course, but what is the Nike sampling theorem? Simply. Huh? Simply speaking, right? Nike sampling theorem tells you this Nike sampling theorem give you a guidance how to select the sampling frequency. You need to select the sampling frequency, right? Let's say you have an A to D converter here, A to D converter. We call this ADC. Input is analog, output digital signals, but inside that we are doing sampling and quantization, and now we are talking about sampling. And how often you sample and what would be the sampling frequency now depends on your input. Now let's think about two different examples. Let's say your input is very slow, like this. Now you need to decide the sampling frequency. Sampling frequency, right? In that case, what you can do is maybe you can do sample, you can get one sample here, and maybe another sample here. Maybe here, maybe here, here. Maybe this is enough, right? Because this is slowly changing. So you can get sample here, 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 right? Then you get, then at the output here, you get this, 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 this. 4 sample only. That's your output. From this output, now the question is, can you recover the original signal? Yes. If you cannot recover, then sampling frequency is wrong, right? If you select the right sampling frequency, you should be able to recover original information. Otherwise, you're losing information, right? You cannot go back. You lost the information otherwise. So in this case, your signal is slowly moving. So your sampling frequency can be also slow. Still, you can recover information, no problem. Let's think about another example. Let's say now your signal moves a little bit faster. In this case, if you use the same sampling frequency, like here, same way, like here, 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 then of course your output is going to be here, 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 here. From this, you can never recover the original information, right? In this case, the best thing you can do probably is like this. That's the best thing you can do, right? You can never get these things, right? Because you lost all the information. In the middle, all this information you already lost when you do sampling. So therefore, if you have this kind of fast-moving sequence, analog signals, what you need to do is you have to use the little bit faster sampling frequency, right? A little bit faster. That way, now you have more samples like this. So when you change it to analog back, then you may be able to recover, right? Okay, so the message here is how often you sample, right? Sampling frequency depends on your input. Slowly moving sequence, you can use a slow sampling. Fast moving input, you have to have a high sampling. Okay, that's simple. But now the question is, we never know what signal is coming, right? We never know. Sometimes slow, sometimes fast. So, but in this case, your sampling frequency of ADC chip needs to be fixed. Because this is hardware. You cannot change your sampling frequency in every time when you get a different signal, right? If you get a slow signal, slow sampling, fast signal, fast sampling, you cannot do it. This is a hardware, right? Everything should be fixed. You should fix your sampling frequency. Yeah, right? So how do you choose your sampling? This is why in every A to D converter, at least you need to know what would be the maximum. Okay, think about this way. What's the difference between this input signal and this input signal? In frequency domain. This is time domain. What about you plot this one in frequency domain? In frequency domain, let's say this is 0. This is a frequency domain. In general, this kind of slowly moving signal has a low frequency. Some kind of low frequency like this. Because low, the low frequency means slowly moving, right? Whereas this one is a fast moving, that means you have a high frequency component. You have some high frequency there. Something like this, right? You have some high frequency component in here. So that's the main difference between these two different input signals. But the problem is we never know what kind of input we're going to get. But at least for your A to D, what you need to do is that my A to D converter can support only up to certain frequency input. And based on that, you're going to decide your ADC. Okay? So for example, my ADC can have the input like, for example, 10 kilohertz. Just an example, right? So that would be the input bandwidth for this ADC. Meaning that if your input signal has a lower frequency here, no problem. But if your input signal is higher than 10, you are going to lose some information. That's a limitation of this hardware. Okay? Maybe you can think about another hardware, another ADC, which support maybe 100 kilohertz. So each hardware has a different specification. But I'm saying this one example of ADC, each hardware has a limitation. Each hardware has an input bandwidth, has some bandwidth that supports your input signal. So if this is the input based on specification, then what would be the sampling frequency you use for this ADC? 20 kilohertz. That would be your sampling frequency. Meaning that if your input, the maximum frequency of your input, okay? Your input sometimes like 1 kilohertz, sometimes. But I don't care. What is the maximum frequency in your input? That's the important thing. In this case, 10 kilohertz is going to be the maximum frequency of your input. And based on the maximum frequency that you can allow for the input, you make it double, which is 20. And that's your sampling frequency. Why do we use a double frequency for your sampling frequency? Simply speaking, right? Think about cosine. Let's say, let's think about cosine. Something like this, right? 2 pi t. What is the frequency of this one? We said this is cosine like this, right? Cosine. Simple sinusoidal time domain signal. This is a frequency 1. Just an example, right? Frequency 1. If we get this kind of signal as an input, okay? My input is this one. Frequency 1 signal. That's coming in to my input. Okay? In that case, what should be the what should be your sampling frequency? Based on Nike's sampling theorem, your sampling frequency should be 2. Why is that? Why is that? Okay, the reason is, think about this, right? After you do sampling, you should be able to recover this original information back. So now let's sample it. Let's say you sample it here, and here, and here. In that case, you are not going to recover, right? Because once you do that, then you're going to get this information. We never know if this one is just this or sinusoidal. We never know. So we are going to lose information. So if you want to maintain the information, I don't want to lose the information. I want to recover the original signal back. In that case, at least you have to make 2 samples within 1 period. What is the period of cosine? Here to here. This is a 1 period, right? 1 period of your cosine. Or maybe from here to here, same thing. So within 1 period of your sinusoidal signal, you need to have at least 2 samples. Here. This one is with this 2, 1 period, another period here, like this, right? Within 1 period, you have to have at least 2 samples. This is a minimum requirement. If you have more samples, that's okay, right? But at least you have to have 2 samples within 1 period. That's the minimum. If you have less than that, you lose information. You cannot recover. So that's why it's 2 samples, right? So that's why you're going to get, and think about now the sampling frequency. Let's say sampling frequency is Fs. Then what is 1 over Fs? If your sampling frequency is Fs, then 1 over Fs is going to be sample duration, like this one. This is 1 over Fs. 1 sample and next sample, what's the duration? And this is 1 over Fs is going to be your duration. And as I said, this is the frequency 1. So what is the period? Period is going to be 1. What is the sample duration? 1 over 2. So this sampling duration is 1 over 2. In that case, what is Fs? 2. So that's why we are going to get double frequency. That's the minimum requirement. If you have 3 times, that's okay. You get 3 samples in that case. That's okay. But the minimum is at least, that's why I say at least you have to have a double frequency of your maximum frequency of your input. Okay? That's the basic fundamental of Nike's sampling theorem. More details about Nike's sampling theorem, I suppose that needs to be covered in DSP course, right? So think about that one. And there's also aliasing problem, but yeah, again, that needs to be covered in another course. So let me just move on. Here's a quantization. That's another step, another process needs to be done in A to D. And as I said, what the quantization does is that you're going to get one of these values. And this function that you are seeing, like a staircase function, tells you how to do quantization. Okay? So here's how things work. The difference between these two is just the shifting this staircase. So basically same. Okay? You see the only difference is moving this one to the left a little bit. So that's only difference. I would see no difference between these two. But here's the idea of this picture. X-axis is input, Y is output, right? What that means is, let's say our input, let's say this is our input. And at some point of sampling, let's say this one has the value of 0.7. Just the example, right? And another sample, let's say we have the value minus 1.5. Let's say that's the value of this one. Okay? So once you do the sampling, you're going to get the value of 0.7. Now this is the input level. Where is the 0.7? Somewhere here. Right? Based on this mapping, this is a mapping. Based on this mapping function, your output is going to be like 0.5. So instead of 0.7, your output is going to be 0.5. So let's draw output here. Now this is your input. This is sampling. After the quantization, you're going to get this output, but you're not going to get 0.7. Instead, this value is 0.5. That's your output. Same thing for the second sample. Second sample, after you do sample, the actual value is minus 1.5, but based on this mapping, minus 1.5 is somewhere here, right? But instead, you're going to get like minus 1.2 or something like this. That's going to be your output. So this one will have this value. So that's your digital signals. And that's how to use this function, staircase function. If you have a certain input value, you get this output. So once you do that, now when you look at this mapping, right, what you can see now is that if your input signal is between 0 and 1, if your input is between 0 and 1, output is always going to be 0.5. Okay? If your input value is between this, 0 and 1, your output is always 0.5. Okay, in that case, now you see that there is an error, right? Original value is 0.7, but your output is going to be 0.5, so the error is 0.2. That's an error, right? Because this is a true value. This is what we call as a quantized value. So there is an error. That is quantization error. So every time when you do quantization, you're going to get the quantization error. Okay? You will have quantization error. As you can see here, right? If your value is like a 0.9, still your output is 0.5. In that case, the error is a 0.4, something like this, right? Your input is between 1 and 2. Your output is like 1.5. Something like this, right? That's a quantization. That's why your output is always going to be 0.5 or 1.5 or 2.5. One of these values. You can never have like 0.9, something like that. You never have it because of that quantization, right? So there is always an error. Now the question is, how can you reduce the error? Quantization error. Error is not good, right? How do you reduce the quantization error? Yes, the simple way to do it is you can have many steps. Each one is a step, right? If you have many steps, like this, right? Like many steps like this. In that case, the error is reduced. Okay, you have a small error. Eventually, if you make a very small quantization step, that's called the quantization step. Eventually, you are going to make a very small quantization step like this. Then it's almost same as like this, right? What is this one? Linear function. What is this one? This one means no quantization, meaning whatever you are getting, you're going to get the same value at the output, right? So that's the ideal case. That's the ideal case, right? Whatever input you have, you get the same output. That's the ideal case. But in hardware, you cannot get linear. You have to have a quantization. But in order to reduce the quantization, the best way is to make your step smaller. That way the error is reduced. But error is reduced, that's good. But what's the problem of these small stair steps? The problem is you have to have so many steps, meaning your A to D converter has to be like 20 bits, 25 bits. The bit of your A to D is increased, right? Which means very complex hardware, very expensive hardware, and very power consuming. Okay, so hardware is going to be very expensive. That's the problem. So there's always a trade-off. You're going to lose something, you're going to getting something. Okay, something like this. So anyway, that's quantization. Okay, this is some basic of how to convert your analog signals to digital signals. Okay. Now what we're going to talk about here is some of the digital modulation. And generally in digital modulation, we can typically think about two different types of modulation. And one type that we are seeing here is pulse modulation. Pulse modulation. And later, maybe next week or maybe 2 weeks from now, we're going to talk about another type of modulation. But this one is a pulse modulation. What that means is we are going to use pulses as a carrier. Okay, now let's go back to analog. We already learned analog. Okay, just to compare with this, right? Let's go back to analog signal. Let's say we have some input signal, MT. That's our message. Okay, I want to deliver this message signal. That's MT, and that looks like whatever. Okay, this comes in to my analog system, analog transmitter, and inside the analog transmitter, what I'm trying to do is modulation. We learned analog modulation, right? For example, DSP. You know DSP, right? Double sideband. So let's say we want to do this, double sideband. What do you need to do? This is input. What do you need to do at the input? Simply, you're going to multiply carrier. Let's call carrier as a CT. Then you're going to get the output, ST. This ST is what you're transmitting over the air. Right? This signal goes over the air. Now the question is, what is that carrier, CT? What does it look like? This is called a carrier. And this carrier, in analog modulation, we were using like AC cosine 2 pi FCT plus phase. Something like this, right? Sometimes no phase, or sometimes there's phase. So let's ignore that to make it simple. So this is the carrier you used earlier in analog modulation. Now the question is, why do you use this signal, why do you use this cosine for the carrier? Why? Yeah, but why do you use this cosine? Why not just use some other signal? Why cosine? That's my question.
Easy to find.
Easy to find what? Huh? Okay. Let me remind you. I think I mentioned that in the previous semester, but let me remind you the reason. The reason that we use a cosine as the carrier is because cosine or sine, that kind of sinusoidal carrier is the best for our channel. Carrier, what signal you use for carrier depends on the channel. Remember the channel that we discussed yesterday? Sometimes you have air as a channel. Underwater can be channel. cable, copper, wire can be channel. Depending on the channel, you want to use a different carrier. Carrier is function of channel. Okay? In wireless air, this is the best way to deliver. Now think about this way. Carrier is like this, right? Let's say I want to deliver my message. Let's say I have some package. I want to deliver my package into my friend who is in Canada. My friend is in Canada. Okay? How do you deliver your package to Canada? Just throw, then it'll go? No, right? So one way is that you use some big ship, and over the boat, right? Over the ocean, it may be delivered. That's one way. Over the air, you can use like a FedEx or any kind of air-based carrier, and they will deliver. So what is a carrier in that case? The carrier is like an airplane or the big boat. That's the carrier, right? Think about channel. In that case, the ocean is the channel or air is the channel. Each one has a different carrier. You can never have an airplane under the ocean, right? You can never have that, right? Under the water, you have to have a big boat. That's the carrier. Over the air, you have to have an airplane. The big ship cannot fly, right? Each channel has a right carrier. Air, this kind of environment, sinusoidal function is the best carrier. That's why we use this one. Okay? So this is the reason. And compared to this, what we are learning now here is exactly same concept. The analog, digital, same thing. Let me see here. Here in the digital modulation, what we are doing is we still have a message. Same message, because the message is same, analog. Original message is analog. Remember that everything starts from the real signal, analog signal. So everything, original starting point is analog, right? Now, what you can do is put this analog signal into my digital TX. Let's call it that way, digital TX. I just want to compare these two. And what I'm trying to do inside this box is modulation. But so simply speaking, modulation is multiplying the carrier. That's what I'm trying to do. But now, what kind of carrier do we use in that case? In this case, what we are going to do is we're going to use pulse train as a carrier. Pulse train. Pulse train. That's my carrier. That's why we call this one as a pulse modulation, right? Pulse modulation, because we use a pulse train as a carrier. Now then, coming back to the original question, why sometimes use cosine as a carrier, and in this case, why pulse as a carrier? And why? What's the difference? Difference is channel. Okay, channel is different. The main thing that in this case is that we are trying to transmit ST over the air, so therefore we have to use a cosine as a carrier because that's the best way to penetrate in the air. Now in this case, apparently you use a different carrier, so we are trying to use different channel. What would be the channel for this kind of modulation? This is like a pulse train, right? Up, down, like high, low, high, low. You can never transmit this one over the air. In that case, it will, if you use this carrier over the air, maybe it goes like 1 meter and it dies away. It dies out, right? So that's not the right carrier for the air. However, this pulse, where do you use these things? Someone probably heard about PWM and things like this, right? Where do you use these things? maybe microprocessor or some like a motor control, something like that, right? So what is the channel in this case? Wire. Think about your microprocessor. Let's say you have a microprocessor and you have some peripherals, motor control or some A to D or there are some other things, right? UART, there are many things. So between chips, there's also chip. Between chips, there's a line, right? There's a copper line. That is also communication. This microprocessor will send some information, like a voltage, right, through this channel to another chip. So it's like a chip-to-chip communication. It's like a communication, right? So in that case, what is the channel? Channel is like a copper wire kind of thing. Inside the board, right, there's a channel. In that kind of channel, it's more effective to use this pulse train, right? It's like a voltage 0, voltage 5, up and down, a logical high low. That's the right way to do it. So that's why you probably heard about PWM or demodulation, but you never hear demodulation used in wireless communication. But you probably hear these kind of modulation when you use motor control, microprocessor. In those things, you hear about these things. Same way, when you do the hardware design, you never hear about this kind of signal. This is not used, right? Instead, this is used. So just remember the difference. Probably the book does not tell you about this, some behind the background, behind knowledge, but that's the some important thing to remember. Okay, just understanding, right? It's easier to remember these things. Okay, given that, now let's look at some of the pulse modulations. We have many different pulse modulations. PAM, PWM, PPM, and all these things. Right? And let's look at the difference between those two. The first thing is a pulse amplitude modulation, and as the name says, your information is in the amplitude. Because this is amplitude modulation. It is actually basically same as your original amplitude modulation in analog. Think about AM, the traditional AM. Example is DSB, SSB. We learned these things, right? And there was also analog FM, PM. Remember these things? We learned this one in analog, right? What is AM in analog? Your information is in the amplitude. If your original information is high, your output is going to be also high. So your information is on the level. Same thing for this one. What's the difference between this AM and this PAM? Carrier is only difference. Okay, everything else is same. Only the carrier difference. Okay. So in this example, AM, let's say your information, original information is this. Your carrier is just cosine. And remember, this carrier frequency is very high frequency. Compared to your original information, FC is very high. So it looks like this, right? Very high frequency. So when you multiply these two, what you're going to get is something like this, right? You still maintain some kind of envelope. Your envelope is still there, but carrier is multiplied. That's your output signal. In here, in the PAM, basically same thing. Your original information is this. That's MT, original information. In here, what you're doing is you're going to multiply the pulse train. That's your CT. That's your carrier. This is your carrier, CT. So MT times CT what do you get? You're going to get this. Okay? Simply, that's your PAM, right? Think about the pulse train as a CT, MT, multiply together, MT times CT, that's going to be ST. So this is ST. Simple. That's very simple like that. You have some mathematics like this, but what this tells you is that when you look at this, then what do you think it is? This is a convolution. Right? Message, here's a block diagram. MT, which is input, goes into modulator, PAM modulator. The modulator has the impulse response of HT. Now the output is ST. So what is ST in this case? MT and HT convolution. Mathematically, that's the same as this. This is convolution. So when you look at the block diagram, that's the block diagram. This is the mathematics. But in visually, this is what's happening. Okay? Same thing. So that's PAM. So again, in the microprocessor, between chip to chip, you can use a PAM. What's the problem with PAM? Why the PAM is not common? There's some problem here, right? That's why the people are not use it, do not use it. The problem is same thing for AM. In analog communication, still the AM is not common. FM is more popular. Why is that? Noise, yeah, noise. Because of noise. Remember that the FM is more robust, more, more stable when you have a noise. AM information is in the amplitude, but noise is adding some value into your signal, right? So that's why AM is a little bit worse. Same reason here. Information is in the amplitude for the PAM. Same reason. So this is not that common because of noise. When you have noise, this is not common. More common modulation is PWM or sometimes PPM. And this PWM, PPM somehow comes together. Some people call that pulse duration modulation, PDM, but I think that terminology is not common. PWM is more common. So what is PWM? In PWM, your information is in the pulse width, not in the amplitude, but width. Okay? So let's look at the picture. It's easier to look at it. This is our original message, MT. Okay? Our MT, original message, like this, right? This MT. This MT is like this, sinusoidal function. Now this kind of MT comes into here. We are multiplying carrier. Again, the carrier is now pulse train. This is a carrier. So you multiply these two, then what do you get? PAM. Okay, that's what we said in the previous slide, right? You're going to get PAM. When you multiply these two, you're going to get PAM. But what about this one? This is a PWM. In this PWM, now the difference is when your original value is high, your pulse is getting fat. Fat, right? Fat. Getting wider. Your original information is getting low, it's slim. It's narrower, right? So that's what it is. So think about that. This is the original pulse, but this going up, right? So that's why it's getting wider and wider. And when you have a maximum value, it's the widest. It's biggest one. And then getting narrower, narrower, and getting come back to original pulse, things like that, right? That's PWM. Now let's say we have a noise. Let's add some noise. We have some noise like that. Actually, typically, whenever we talk about noise, we always talk about a additive noise. Do you know what that means? Additive noise? What that means is noise is added. This is our original, this signal is ST, right? ST, like this, ST. This is what we get after the modulation. Now we transmit this one over the channel. In this case, our channel is between chip to chip. That's a channel. In between channel, noise is being added. So ST, now noise is added, like noise. And what you're going to get is ST, which is this one, or plus NT. That is what you receive in the receiver. What I'm saying receiver in this case is another chip. It's like chip to chip, right? So this is a transmitter chip, receiver chip. Transmitter chip does these things and transmit ST. Over the channel, noise is added, right? That's why we call this additive noise, added. This is what you receive at the receiver chip. Once you receive that, what is a noise? Noise typically looks like this is 0. I'm only drawing the noise. This is just noise. Noise is always like this, right? Noise is a completely random signal. This is ST, right? After you do modulation, you create the ST. And when you use a PWM here, if you use a PWM here, you're going to get this one as ST. So this is ST. Now we have some random noise. Let's add these two. Add these two. What do you get? You're going to get something like this, right? That's what you're going to get. That is what is going into the receiver chip. Okay? And from this, we have to recover original one. So we have to remove the noise and we have to recover the original ST. So that is what is coming. Okay, anyway, so this is a PWM, pulse width modulation. What is this one? This is called a PPM, pulse position modulation. Pulse position modulation. In this particular case, your information is in the position. PAM, your information is in the amplitude. PWM, your information is in the width. Right? When you look at the width, you know the information. Width is fat, some high value. Narrow, low value. Right? In this case, your information is in the position. You see that the pulse is in a different position. How do you know? As I said, this is the original carrier. Original carrier, right? So think about the original position of the carrier. Original pulse was here. Now this pulse has moved, and now the new position is here, right? It actually moved. Same way here. Actually, same way, like that. Something like this, right? Something like that. So what you can see here is that compared to the original position of your pulses, now in PPM, each pulse is in a different position. Their width is original, is same. The pulse width is same as original, right? It's not fat or thin, it's the same. And amplitude also same. Only the change is the position. When you have high value, it actually moves a little bit further. Now see, you have it moved this much. And in this case, it moves a lot, right? This one was, here it was original information, but this one actually moved a lot. Why? Because we have a high information, high value. Whereas if your value is low, they actually moved a little bit, right? So depending on the position, now you have a different value. That's ppm. The ppm is not common, not that common. Again, you can use this one like a between chip to chip communication, but that is not that common. Why is that? Think about the receiver. When you use this ppm at the transmitter, receiver has to detect where is this pulse, because that has information, right? But it's a little bit difficult to find the position. Think about hardware, right? It's not easy to do it. Also, the timing may have some error, right? Timing actually drifts in hardware, right? Yeah, so it's not that common. But anyway, ideally speaking, amplitude may have information, pulse width has information, or position can have information. So those three are different pulse modulations. This one is a quantization process. I think we already discussed this one. And what this slide tells you is that, again, the input-output relationship. If your input is between this and this is mk minus 1, meaning that, remember the quantization, the staircase? So here's mk, here is mk minus 1, or minus 1 mk, something like this. So if your input is between these, right? If your input is between these, right? Then your output is going to be some other things. Your output is always going to be one value. Your input is between here, your output is always one value. So that's what it is. And quantizer is, this is quantizer, the staircase step, right? So this picture also shows you that if your input is between mk and mk plus 1, it doesn't matter. Maybe your input is here or here, it doesn't matter. Your value will be only just one value, same value. So far we looked at some of the basic pulse modulation, PAM, PWM, PPM, right? And these things is something a little bit more advanced compared to the PAM, PWM, right? Yeah. Okay, maybe we can stop here and we can continue next week.